Good morning, everyone. Today is February 16th, 2016, and this is our lecture 8. Actually, this is also our first online lecture, and it's the first time I record my lecture with OneNote. And this sounds a little bit different, and it feels different, but everything has a first. So previously, we have studied we have introduced the concept of field, which is a function of space and time. Space means x, y, z in Cartesian, or r, theta, phi in some different coordinate. Time, of course, is just time. And in fluid mechanics, the most important field is the velocity. And velocity can have three components, u, v, w. Each one can be a function of space and time. And this quickly becomes a very complicated variable, and later we'll see to operate on this velocity is going to make this even more complicated. So we are mostly interested in the very, 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 very special case. In this case, we have only one velocity component, and this velocity component is the only function of y, but its direction, for example, and this is our I or x direction, and this is our y direction. The velocity only has x component, but it's changing along the y direction. The most typical example we have used is flow between two parallel plates, something like this. If we draw it in 3D, we have two plates, and we will have this kind of velocity profile, and this is our x direction and this is y direction. And we call this as unidirectional flow. And in this unidirectional flow, the velocity only has one component, and this velocity is dependent on y. Okay, so the next important concept we are trying to explain is the flow rate. And this is very, very important, and we're going to do a lot of math, and sometimes it's quite complicated to get the flow rate through the math. So let's consider a very special case. Let's say if we have a cross-section, let's say a square cross-section, and the area is A. And across this square, we have a uniform velocity, which is u0, let's say. And now, if we ask you, what is the flow rate? And more precisely, it's the volume flow rate through the area A. And how do we figure out this problem. So if we are on a face-to-face class, I will pause and ask you to think about this. Now I will probably ask you the same thing. You can pause the video and think about how can you figure out the flow rate if we use the Q dot to denote it. How can we figure out the flow rate? Okay, the flow rate is the change of volume with respect to time, right? And the volume is some cross-section area times some lengths, and then divided by time. The second term here, if we divide it by the time change, that will give us the velocity. Therefore, the flow rate for uniform flow perpendicular to an area is like this: velocity times area. Okay, this is important, and we need to memorize this. So I give it 3-star designation of importance. And there is a conversion of mass flow rate to the volume flow rate. If the mass flow rate, we write that as m dot, then it is just mass density times the volume flow rate. And this, we can also derive this in a similar fashion, because m dot is equal to dm dt. dm is equal to density times volume and dt, and of course this is q dot. Okay, the important thing about this equation, these two equations, is although our flow rate may not be uniform, but for any small area element, velocity is going to be uniform. Therefore, the dq element will be the area, which can be a function of location, but it's still going to be uniform, relative uniform, for this very small area dA. So for small area element, our dq is going to be to satisfy the same equation we just derived before. So this actually is more important than the one we just wrote. So this equation, the flow rate equation, flow rate element equation, allows us to figure out the total flow rate for a more complex flow field. For example, if we want to figure out the flow rate in parallel plate flow, in this case we have two parallel plate. Okay. Their separation is h, and the width of the plate, let's call that B, and the top plate is moving at a velocity of u0, and the bottom is fixed. So we'll have this kind of a velocity profile, and this velocity profile is the same for every location. For example, it's also the same for the cross section on the back, and the same for everything. Basically, we are looking at a prism or at a wedge shape of velocity profile here. And this is our x direction, and this is our y direction. In this configuration, we can write the velocity profile as u0. Right. This will satisfy when y equals 0, velocity equals 0. When y equals h, velocity equals u0. Excuse me. So, how do we figure out the flow rate for this flow? Well, we are going to use the equation which is derived. So the total flow rate will be the integral of the flow rate, and then we use this equation, uy and dA. In this case, what is the dA? The dA is just a little stripe we have here. So the length is dy, so the area will be the width times the height of this little stripe. Then we put everything together. U is equal to y over h u0, then times b dy. See, this is our dA, and this is our uy, and this is our dq. And the integral is from y equals 0 to h. Now we have this constant, and this as constant. So we pull all the constant out. What we have is y dy. And this, of course, is going to give us half y squared, and that's from 0 to h. Therefore, we have h u naught b times half h squared, that is equal to u naught b h divided by 2. Okay, so let's check the unit. Velocity times area, that will give us a unit of volume flow rate. So this velocity, this volume flow rate, at least from the unit point of view, it's correct. Now let's introduce the concept of average velocity. Average velocity, let's say u bar. Keep in mind this is different. This is not a vector. In vector here we have a little arrow here, but for bar we just have a straight line. So for U bar, we define that as the flow rate divided by area. So if we have the unit flow rate, uniform flow rate velocity profile, then the average velocity will be the same as the velocity. But if we have this linear velocity profile, then it's going to be slightly different. So for this case, let's say for this case means our U is linear, U naught y over h. This U is equal to Q dot, we have half U naught B h divided by area. Area is width times total height. So we have half of the peak velocity, which is at the bottom. So for linear velocity profile, the average velocity is exactly half of the velocity, peak velocity. Now let's look at a slightly different case. In this case, we still have a pair of parallel plates, but in this case, the flow is in a way that it is parabolic. Okay. The separation is still h, and let's say our velocity, if we choose the center as y equals 0, this is our x. The peak velocity, we call it U max. Okay, so the velocity profile in this case is U max times 1 minus y divided by half h squared. Okay, this velocity profile will satisfy when y equals half h, U equals 0. When y equals minus half h, U is 0 as well. Additionally, when y equals 0, which is the center of the flow, U is equal to U max. So this velocity satisfies all the critical point, top, bottom, and center. So now we ask you, oh, by the way, the width of the plate is B. Now we ask the flow rate. If you don't specify it, it's going to be volumetric flow rate. If we ask the mass flow rate, we will specify that we want mass flow rate. So flow rate as well as average velocity. So what do? Flow rate is equal to integral of flow rate and integral flow rate is uy times dA, and our uy is umax times 1 minus y square h square divided by 4 times b dy. This is our dA. This is our uy. And this is dq. And y is from minus half h, which is the bottom, to positive half h. Okay, so the math now is a little bit more complicated, but it's still very doable. We take all the constant out. One minus 4y square h square dy. And what's inside here is y minus 2y, no, actually 3, 4 over 3 y to the third power. Let me rewrite this. So 4 h squared, that's the coefficient of this, and then 1 over 3 y to the third power. And this part is being integrated from minus half h to positive half h. So we have h minus 4 h squared over 3 and 1 over 8 h to the third power and times 2, because we have positive and negative, so that gives us 2. So this end up with 2/3 of h. So this integral is 2/3 of h. Therefore, BH. So this is our flow rate. And again, if we check the unit, it's velocity times area here, and then it's going to be to give us the unit flow rate. Now the average velocity u bar is q divided by the area, which is a rectangle formed by B and H. Then this will give us 2/3 of the Umax. So this should be something expected. For example, if we want to figure out the average velocity of a linear velocity profile versus this parabolic velocity profile, and we both use the maximum velocity as the reference, obviously this parabolic velocity profile is going to give us higher average. So the average here is half of the U max, but average here is 2/3 of Umax. If we figure this velocity, average velocity as half of the Umax, then something may be wrong. We can make this a little bit more complicated. So before what we studied is the cross-section is the rectangle or infinite long, infinite wide space between two parallel plates. And now let's look at the circular pipe. For circular pipe, if you imagine the velocity profile inside and we draw the symmetric line here, it's also going to be parabolic. We will derive that later in this class. So it almost looks like a bullet. Okay, this is a little bit, it looks like a 3D view. And if we just look at this in a 2D view, it's not easy to distinguish this from flow between two parallel plates. You see, this and this are similar but different. First of all, for a circular pipe, we usually will draw long and short dashed lines to indicate the axial the axial symmetric configuration. But for the parallel plate, we just don't have that. Okay. So, and secondly, the average velocity is going to be different. So in this case, we can give you the velocity profile. Now the velocity is going to be a function of r. So this is still x, but this is r. And the radius of the pipe, let's say that's a capital R. If it's a parabolic, we will have a peak velocity, which is Umax here. And then it will have this form. So in this form, it satisfies all the key boundary condition. When we are at the wall, the velocity is going to be 0. When we at the center, which r is 0, then u is going to be Umax. Okay, so from this point of view, it's also very similar to the flow between two parallel plates, if that's a parabolic. But what's different is the total flow rate. Okay, so first of all, the dA. dA for a circular pipe is different. So if it's a rectangle, dA is b times dy. Right? Basically, this is a stripe. But for circle, dA is 2 pi r dr. So this is for a ring. So if we have this ring, and its radius is at r, and the width of this ring is dr. So the circumference of this ring is 2 pi r, and the width is dr. So 2 pi r dr will give us this dA. So for circular pipe, we have to use this area. So that is the main difference between a rectangle channel. Now we're ready to do the flow rate. Q is equal to integral of dq, and that is also equal to uda, and that is u max to pi r dr. So this is u at the location of r, and this is dA. Keep in mind our integral is from r equals 0 to r equals capital R. It's not from r equals minus r. That is not correct, because we can, for cylindrical coordinate, we can only start from here and then go all the way to the wall. Then we take the constant out. This is constant, this is constant. So u max 2 pi, and then what do we have inside is r minus r third power r squared dr, and that is from 0 to r. So this gives us half r squared, and this gives us 1 over r to the 1 over 4 to r to the 4th power, and then r squared. And this is, the whole thing is from 0 to r, and then this is 1 over r squared. So basically this whole thing is 1 over r squared. So the flow rate okay. Now the average velocity, u bar is q dot divided by area, and this area is a cross-section area of the circle, which is pi r squared. And if we put this here, very easily we're going to see that the average velocity for a pipe that has parabolic velocity profile is half of the u max. Okay, so this is different from the rectangular flow in a parallel plate. Let's summarize this. So for rectangle, linear velocity profile, q dot is half, say this is u max, half u max times b and h. U average is half of u max. Again, if it's parallel plate, flat plate, and we have this parabolic velocity profile through and through, this is like a trough. Okay. The flow rate is 2/3 u max bh, and u average is 2/3 U max. But if we have a pipe, now the velocity profile is like a bullet tip. Okay, this and this, those two are not the same. Now the flow rate is U max times half pi r squared, and the velocity, average velocity, is 1/2 of maximum velocity again. Okay, so today it's the first time we use this, and we're going to keep it short, so we can ask questions if you have any questions next time we have the face-to-face lecture. All right, hope you enjoyed.